Alright, I'm making this video because I'm learning about electronics and I don't want to forget what I learned, and this might be useful to somebody. I don't know. So what I'm learning now is how to manipulate a 555 timer which produces a tone. I'm manipulating it with two digital potentiometers, 4131. The 555 timer requires two resistors, R1 and R2, and I'm using the digital pots for that. Okay, so what I'm doing is I'm keeping a constant value for R2, and I'm making R1 rise from 0 to 128, which is the range of values that these 4131s understand. When the value is 0, then the resistance should be 0, but there's actually a wiper value of 75 ohms, and when I tested it, it was actually 87. And when the 4131 receives a value of 128, which is maximum, it should be a resistance of 10,000 ohms. It actually turns out to be pretty close to that, but 240 ohms short, so 9,760 ohms. So here's the Arduino program that I wrote. R1 will rise from 0 to 128. R2 will have a constant raw value of 128. Here goes. Okay, so you probably noticed that when R1 was equal to 0, there was no sound. So there should have been a sound, but there wasn't. When I've tested the 555, it seems there's a bit of an anomaly. It acts strangely at the values that are close to 0. In fact, maybe you noticed that as these numbers were increasing, R1 was increasing 1, 2, 3. The frequency is supposed to go down, but maybe you noticed it went up. That's part of the anomaly. Okay, we have silence at 0, and we have the frequency going in the wrong direction for the first few values. Here that is again. Yeah, so anyway, that's weird, but that's what it is. That's what this testing is all about, is learning about these weird things and how it all works. So I'm going to make that happen faster so that we can hear what happens after that. Here goes. As you can tell, the pitch is dropping as R1 is increasing. That's just going too slow. I want it to go faster. And maybe we will also print out the frequencies. I'm going to print out the calculated resistances and the calculated frequency. It's not accurate, okay? This is according to the formula right here. But the 555's behavior is, or I should say actually, the 4131 and the 555 seem to have their own little non-linearities. So the calculated values that are going to be displayed are not really accurate, but it's good to know what they are. So as you could see over here, as R1 was increasing, the calculated frequency was decreasing. It started out at about 1 kilohertz when R1 was 0, supposedly 0 ohms, but not quite true. All the way down to 705 hertz. Alright, so we can make the R1 value fall instead of rise. That should make the frequency rise instead of fall. I hope I didn't say that backwards. Just have to upload the program after changing the variable. Here goes. R1 will fall. R2 is constant. The frequency is going to rise. There it is, rising. Okay, what I also wanted to do with this testing program was to be able to scale the range. So instead of going from 0 to 128, maybe you could go further than that. We could scale it larger, twice as large, so that it goes from 0 to 256 instead. So let's do that. Here it says, R1 range will be progressively scaled around 0. We'll get into that pretty soon. The range will be expanded. Any values of R1 shown in asterisks have been exceeded the maximum range of the 4131 can only handle input values from 0 to 128. So when the value goes beyond 128, it gets clipped, which means that the 4131 will understand 256 as being 128 instead. Here goes. Okay, that's going too slow, but I just wanted to show you what started to happen there. The scaling sequence starts out by just going normally from 0 to 128, 0 to 128, and then it starts to scale that range by increments. It scales it to 125% of that range, which goes from 0 to whatever it goes to. I interrupted it. But I'm going to do it again, and it's going to go faster, and it's going to go through the sequence of percentages. 125%, 150%, 200%. And I'm just going to turn off the printing of the frequencies and the calculated resistances. Here goes upload the sketch. So the range from 0 to 128 will be scaled in 4 levels. Okay, so by the last iteration of scaling, which is the ratio of 200%. You can see that R1 went from 0 to 256, and as soon as it started to exceed 128, the values became clipped, which hopefully you noticed resulted in a sort of flattening of the frequency for the last half of the last progression. Let's hear it again. You can hear the flat spots. You can hear the flat spots where the tone falls and then stays the same for the last bit. So I also wanted to be able to scale the range 0 to 128 around the median. So the median of 0 to 128 is, or the center, which is 64. So with that as the center point of scaling, it scales up and it scales downward beyond below 0 and above 128. So both of those things are going to get clipped. And I call that scaling around the median. So I'll just change that right now. Scale around the median. Here goes. All right, so by the last level of scaling, 200%, you can see that the R1 value dipped below 0 to the amount of minus 64. And during all that time range when it was below 0, there was a flat spot because it got clipped. And then as R1 changed from 0 all the way up to 128, then we get a lowering pitch, and then once it clips beyond 128, it was a constant pitch. Let's listen to that again. Okay, so when R1 was clipped below 0, remember that there should have been a constant pitch, but that the 555 timer doesn't produce a pitch when R1 equals 0. So there was actually silence during those portions. But we still did get the flat spot in pitch when it goes beyond 128. Okay, another thing I did with this program was I wanted R2 to change automatically in relation to R1 in such a way that the frequency would be constant. So as R1 is changing, R2 has to change by half that amount because of this number 2 coefficient right here. And so I built that into my program. So we're not going to keep a constant R2 this time. R2 is going to automatically change. Here it says R1 will rise from 0 to 128. R2 will be automatically adjusted to attempt constant frequency according to the 555 timer's frequency formula. Here goes. Okay, well that was a fairly constant pitch that sort of had a bit of a curve to it at the beginning and at the end. That's for two reasons. I think it's because the 555 anomaly had its extremes, but also because I made my math go according to like perfect formula, and I didn't account for I didn't account for the inaccuracies in the 4131, such as the wiper. I forgot to include the wiper, theoretical wiper value of 75 ohms, and I definitely did not include any compensation for the actual measured values. So instead of using the range of 87 ohms to 9,760 ohms, I just made it go the theoretical distance of 0 to 10,000. So, so for that reason, the pitch wasn't exactly, the frequency wasn't exactly level. Let's hear it again. Notice there's also a flutter. I'm going to slow this down quite a bit, and we'll be able to hear that when it does stay at a fairly steady frequency, it actually bumps up and down a little bit every time the value of R1 changes. And that's because the 4131 accepts integer values for its control, but when we change R1 by a value of 1, we're only changing R2 by a value of a half, and that precision gets lost in the integer conversions. So that causes a bit of an up and down flutter every time the R1 value changes. You can hear the pitch go up and down just a little bit. Here it goes. You can slow that down even more so you can really hear the, I mean, that's a very audible flutter. But if we slow it down, we can see how it corresponds to the changing R values on the screen. So you can see that for every 2 R changes of R value, R2 only changes once. So that's why we get the fluttering up and down. So that is my video. Oh, no, it's not. So I forgot to explain one of the reasons for keeping a constant F frequency. I am going to eventually design some synthesizers or something. I don't know. But I wanted to hear with a constant frequency the effect of changing R values, because what happens is when these two R values are changing in relation to each other, the duty cycle changes, and that is an expression of how wide the half of the square wave is. For lack of a better description, it's something like that. So it should change the sound gradually. So I'm going to print out the duty cycle. And we can see the duty cycle printed out, and see it changing as the R values are changing. Here we go. So after the anomaly was surpassed, that happened in the first few values of R1, then the frequency did start to level out, and you could also see that the duty cycle is gradually increasing. I'm going to speed this up quite a bit. Now this is just a piezo creating the sound, but sometimes I like to hook up an audio jack and record it. And so I wonder if that might reveal a more obvious sound change when we have a changing duty cycle. But maybe you can hear that right now. Here it goes. I mean, we definitely got that flutter that's very noticeable, but the changing duty cycle, maybe you could sort of hear it. With my other experience of duty cycle, I would say that a 50% duty cycle is a thicker sounding square wave, whereas anything that goes more towards 0 or 100% is a sort of thinner, buzzier sound. Here it is again. Okay, well that's about it for my video.